Yes, okay. So welcome everyone to this week's Applied and Computational Math Seminar. For the first time this term, we're meeting online. And today's speaker is Katriel, who's an associate professor at the ORT Braude College in Israel. And as I checked online, Guy did his PhD at Technion, Israel Institute of Technology, then had a spell of postdocs, some in Israel, some in Germany, and also brief visit to UBC in Canada. Then he was a lecturer at Tel Aviv, and now he was first a lecturer, now is associate professor at the ORT Braude College. And today he's a renowned expert in operator theory, but also in epidemiology, the mathematical aspects of it. And today's talk will be about the latter topic. And so Guy will be talking about thinking about COVID with mathematical models. So Guy, thank you for joining us, and it's over to you.
Thank you very much. I'm really glad for this opportunity. And thank you for the invitation and for your introduction. First of all, I'd like to say, please feel free to, if you have comments, questions, just speak up. I'd like to thank my colleagues who I've been working with since the start of the pandemic, and actually some of them since the previous pandemic in 2009, the swine flu pandemic. I'd like to start by, so I'm going to discuss epidemic models, and start by saying that epidemic models are used for different purposes. So I think that in a sense, the most important is that they are tools for thinking. They allow us to, they give us a framework to think about the implication, the population scale implications of individual behavior and processes. We also use them to learn from data. So these models contain some parameters which are interesting in themselves, but it's hard to estimate them directly. So by fitting the models to data, we can learn about these parameters. Of course, we would like to use the models to make some predictions or projections of what will happen in the future, and also to help plan for the future, so we can simulate different interventions, vaccinations, lockdowns, whatever, inside the model, and maybe can help us to make decisions. So since there are different purposes, we also need different types of models, and there's this distinction which I think is useful, made by famous ecologist Waning, between strategic models, which are aimed to be as simple as possible, just to capture the essential mechanisms, and even if they distort reality in many ways, and what he called tactical models, which are complex. They try to capture as many, to be as realistic as possible, and we'll see both types of models in this talk. So what I'm planning is to talk first about some really basic models, which are the foundation of this field, and see what are the essential insights that they give about epidemics. Then I'll talk about, describe some recent work that we've been doing on fitting models and studying what is happening in Israel. And if time permits, I will talk about thinking about the future, the longer term future, using simple models. So I want to start at the beginning with these are like the fathers of mathematical epidemiology. So what I'm going to describe in this part will be the basic SEIR model, which I suspect that most of you are familiar with, that you've looked into this field a bit, but I don't want to assume. So I'll just go forward and just build this simple model from the bottom up. And okay, you see that this work goes back to 1927. I guess it's not an accident that it's just several years after the big influenza epidemic, the Spanish flu, which was the biggest pandemic so far. Oh, I have some problem. Oh, okay. So I'm going to build the SEIR model. In this model, we have the three compartments of susceptibles, infections, and removed. And we have only two processes that we need to consider. That's infections going from S to I, and recoveries going from I to R. To describe the infections, we introduce the two parameters, which is the average number of contacts of an individual per day, and P, the probability of infection upon contact. So the product of these two is actually what comes into the model. It's the average number of people, susceptible people that one infected individual infects per day, if all his meetings are with his or her meetings are with susceptible individuals. And but as the epidemic progresses, many of the meetings will be with those who are already infected or have already recovered. So if only 50% of the population is susceptible, then only 50% of these contacts will lead to new infections. That's why we have so the number of people this person will infect is beta times the fraction of susceptibles, current susceptibles, and so the total number of infections per day is this times the number of infected people, and we have our description of the process of infection. And if for recoveries, we do a very problematic thing. We assume that in this model that the chance of recovery is the same every day for an infected person. So it's just a constant. The number of the recovery is just a constant times the number of infected person. This constant is 1 over the average length of the infectious period. Okay, this is not that realistic, this constant probability assumption, but that's this model. So we have the infections, we have the recoveries. So we can write the differential equations for the change of the number of susceptibles by infections, the change in the rate of change in the number of infected by infections and recoveries, and the change in the number of recovered. And we have the model, we can simulate it. We can't really, even this model, we can't exactly solve in closed form as a function of t, but we can simulate it and generate epidemics. One small thing that can help the analysis is to divide everything by n, the size of the population, so you get equations so the new variables are just the fractions of each of the groups, and you see that it doesn't matter. The size of the population doesn't really come into this model, just the fractions of the populations. Okay, There are lots of assumptions implicit in this basic model. For example, we don't take stochasticity into account. It's a stochastic process, of course. We assume homogeneity, everyone is the same. The mixing is homogeneous, everyone meets everyone. So there's no spatial element. This constant recovery probability that I mentioned, we don't have an incubation period. And this transmission rate is constant. So, okay, in reality, if we have a lockdown, then beta changes, which we should consider beta as a function of time. But still, this basic model gives some crucial insights about epidemics, I think, and I want to list them. So the first one is this notion of epidemic threshold. So if you look at time t equals 0, let's say when the pathogen was introduced into the population, and we look at the equation for the number of susceptibles, we see that it will increase if this expression is positive. This expression being positive, we can write it in a different algebraic form like this. And if we introduce this R0, the basic reproduction number, beta over gamma, then we can write it like this. And if we're talking about a new pathogen, so everyone is susceptible, then the threshold condition is R0 greater than 1. And so if R0 is not greater than 1, then the epidemic will not spread at all. There won't be any epidemic. Okay. And there's this R0 can be interpreted very simply because R0 is beta over gamma, and 1 over gamma is the average infectious period. So R0 is the number of people that an infected person infects per day, if in a totally susceptible population, times the length of time during which the person is infected. So it's actually the number of people that an infected person infects during the whole period in which he's infectious. And this inside the threshold insight has a implication about vaccination, because if we can get this product of R0 and the initial fraction of susceptibles to be less than 1, then we won't have an epidemic. So to get this to be less than 1, we just need to vaccinate enough people, so that this product is less than 1, and this is the what is called the herd immunity threshold. Okay, it's the basis of all the idea of vaccination, that you don't have to vaccinate everyone in order to eradicate the disease. So let's say if R0 for coronavirus is, let's say, 4, then you need to vaccinate 1 minus 1/4, 75% of the population to get this herd immunity. This here I will, this becomes more complicated, or if you want to be more precise, if you take into account the fact that the population is not homogeneous, then you have to and you divide it, let's say, into age groups. That's the most important heterogeneity. Then you can exploit this fact, this inhomogeneity, to vaccinate in a smart way, to vaccinate the people who have more contacts, let's say, or more important for the process of transmission, and get better results. So here I'm going to digress a bit from the simple model and just mention the extension of this model to n groups, to different age groups. So you just have n age groups, and they're all coupled together. So you have this matrix C, which is the average number of contacts of a person in age group J with people in the other age groups. And then you have a condition for herd immunity in terms of the spectral radius of some matrix related to the contact matrix, and you can manipulate the number of susceptibles that you will vaccinate in each age group, and ask questions like what is the optimal thing to do. And we've done a lot of computations on this question. So what you see here is, for example, if you look at the middle panel, so we have for each value of R naught, we do a numerical optimization to find what is the allocation of vaccinations among age groups that will allow to reach herd immunity with the smallest number of vaccinations. So what you see here, actually, if you look at, for example, at let's say R naught equals 3, you see that the optimal, the least, to achieve herd immunity with the least number of vaccinations, you would actually you would not vaccinate the older people at all. And so this is not what was done, and what I think it's wisely, because if you aim for herd immunity through vaccinations, and if our calculations are wrong, if our estimate of R naught is wrong, if something is wrong, if you leave all the older people unprotected, then you're in a very, very bad situation. So the policy in all countries was to not to go for the herd immunity, but first of all to protect the most vulnerable.
Sorry, can I ask? So
Sure.
does this have anything to do with, let's say, that the older people have less contacts? Is
Yes,
that,
yes,
okay,
yes.
yeah.
The reason behind the fact that they, okay, you don't vaccinate them until higher values of R naught, then yeah, it's because they have fewer contacts. Yeah, and okay, I have to say, I'll mention later about how this matrix is. We have to estimate this matrix of contacts in order to do all these calculations. So there are various ways to do these estimates.
Okay, thank you.
Could I ask something too quickly?
Sure.
This age group 70 to 79, why does it start at this very high R0 value? Why doesn't it look like the other ones? Is there an intuitive reason?
Why 70 to 79 starts, let's say, later than 80, than the 80? I can't answer. I think we noticed this. Okay, so basically, I guess the reason is because the matrix says they have fewer contacts, but why would they have fewer contacts? I don't know. Maybe I think we had some. Maybe the 80 plus are more in old age homes, so they have more contacts, or but I don't know.
Okay. Thank you.
Observation. Another thing I'd like to mention is this, going back to the simple model, is this, okay, the exponential growth at the start of the epidemic. So here you see the start of the pandemic in different countries on a log scale. So it's a straight line at the beginning, which means it's exponential growth. And okay, again, from the equation, if you assume that at the start the number of susceptibles, you can treat it as constant, because the depletion of susceptibles is not significant at the start. So you just replace this by 1, the fraction of susceptibles, if everyone is susceptible, and you have this. So you see that beta minus gamma is the exponential growth rate, and you can turn it back and use this to estimate the R naught in terms of this exponential growth rate, which you measure from the data, and in terms of the 1 over gamma, which is the length, the period of infectivity, which you can estimate from the clinical data. So you have so for example, for coronavirus, let's say the doubling time is 3 days, the exponential growth rate is 25% per day. That's in unmitigated situation where and let's say the duration of infectivity is around 5 days, so you can get this estimate of 2.25 for R naught. So these were the initial. This is how the R naught was initially estimated, and it was the results were between 2 and 3. Now it's about twice that, between 4 and 6, because of the delta variant. One last general insight is that epidemics don't infect the entire population. And this was actually kind of a mystery before the models were developed. And people saw this, that epidemics end before the whole population is infected. So here you see the recovery. So it doesn't go to 100%, it goes to here to 80%. So there were also even some theories like that the pathogen weakens when it passes from one person to another, and that's why that's the reason it doesn't infect the whole population. But actually, when you go to the model, you see it comes out from the model. The epidemic dies before infecting everyone, and you can even there's even this called final size formula, which you can derive very simply from the differential equation. It's like an equation so Z is the total number, the fraction of the total fraction of the population infected, called the attack rate. And you have this transcendental equation, which you can solve. Okay, depends on R naught. For every R naught, you have a different final size. Here you see a graph of the final size as a function of R naught. And below, it's the herd immunity threshold that we discussed before, that how many you need to vaccinate to prevent the epidemic. But it's also the number of people who are infected, who become infected up to the point where the epidemic reaches its peak. It can be seen. So the gap between these two is like the people who are infected when the epidemic is going down, but it's a significant gap. So okay. Last thing I'd like to mention that I think that the simplest model that has been routinely used for the coronavirus is the SEIR model, where you add this latency period. So it's a period when you get infected. There's a few days and before you become infectious. So this is important. I'll show you that it makes a difference. So here is the red line is the SEIR model, and when you add the latency, the 3 days of latency, the epidemic becomes shallower and longer. But you see that the final size is the same. This is the number of susceptibles at the end is the same. So the same final size formula still works. It doesn't change the number of people who eventually get infected. This can be shown easily from the equations. Okay. So now I'm going to describe some things that we've been doing. So I have to tell you some history of what happened this year in Israel. Vaccination started just at the start of the year, start of January, and we had a very rapid vaccination campaign. We reached something like 60% of the population by March, and the cases went down so that at the end of May we had almost 0 cases. And then in June, we started seeing an increase, rapid increase in cases. And it was clear that that it was not going to go well. And we looked at the data, and we were shocked to see that this result, that what this shows is the okay. Let's look, for example, at the 60+ age group. This shows that the rate per thousand during this period in July, and it's stratified according to the date of vaccination. So you see that the people who had been vaccinated in April, May had much lower rates of infection than those infected in January and February. So what this shows is the waning of the vaccine. We had the Pfizer vaccine, and I think this was the first time this was shown in the world, because we had an early vaccination campaign. So we reached this point of waning immunity, and the first country to reach this point. So by the end of July, the decision was made to do a booster campaign, and this was also kind of a bold decision because no country done it, and there was no regulatory approval from FDA or anything like that. And so this shows the booster campaign, which started at the beginning of August. And okay, the older people, almost 90% of the older people were vaccinated. In the younger age group, less people took the vaccine. And we wanted to model this, to have a model to predict what would happen, and to study, to describe this waning of the immunity and this booster campaign. And I want to describe briefly what is the type of model that we use. So we're not using this SEIR model. We're using a different sort of a different framework, which is called the age of infection model. So first of all, let me describe this. This is a discrete-time model, but that's not the main thing, because you can formulate this model also in continuous time, but it won't be a differential equation, but an integral equation. So what this describes, so the I of t here is not the I of t we had before. The I of t before was the prevalence, was the number, the number of infected people. Here, the I of t, the I small of t, is the number of new infections each day. It's the rate, not a flow. It's a flow, not a stock. So what you have here, and this P of tau is called the generation time distribution. It just describes if you become infected on day 0, how many people will you on the average will you infect on day 1, on day 2, on day 3. This way you don't have this assumption of a constant infectious period. You can use the data. So here we have, this is the generation time distribution that we used, and it's based on epidemiological investigations, where we know that how many, we know that this person infected this person, so we have the statistics on the number of days, and so this is how we so the number of people that will be infected on a certain day is we sum over all the previous or some previous days, how many were infected tau days ago times how many people they will infect today, and okay, times this S of t over n is because some of their meetings will be with non-susceptible people. So this is called an age of infection model, and it's more realistic in a sense. And how do we fit it to data? So we have some parameters which we need to estimate as part of this of fitting the model to data. And what we do is we have an observation model which we model how the observational data, which here is denoted by I bar, is related to the real number of infections. So here we just assume, okay, we have some detection probability, which not every case is detected. So this is the relation between the number of cases in the data is the number of cases given by the model, or is a binomial variable with there is some probability that the case will be detected. The advantage of introducing this probability thing is that we can construct a likelihood function, which is the basic method in statistics, and it's a function of the parameters. So theta denotes the parameters. Each time we want to compute this likelihood function, we have to run the model with these parameters, generate the simulation, and then compute the likelihood function. And this is numerically optimized to find the best fitting parameters. This is the idea, standard idea. Okay, of course we extend this to age groups like before. We have data for each age group. And this contact matrix, this contact matrix is this is a representation of the contact matrix. It's based also on epidemiological investigations of who infected who. You see, these matrices always have this structure. You have a strong diagonal, like interactions in this similar age groups, and then you have these sub diagonals. It's children and parents. Okay. So we, in order to describe this waning of immunity, we had to also to include this waning into the model, and also the booster campaign. So complicates the model, but I won't go into details. But we fit the model to a lot of time series. So we have 9 age groups, and for each age group we have those vaccinated, the unvaccinated, the vaccinated with 2 doses, and the vaccinated with the booster. And we also have both detections and severe cases. And we only estimate a few parameters. Here, what you see here is based on the data that we have available, the waning of immunity. See, it's pretty bad. So this is based also on data from the literature and on our own data. It goes down very low after half a year or so. The waning is really strong, about 10%. The efficacy goes down 10% a month. So, okay, so once we have all this model, I'll show some results. And this is like, okay, we did this in real time, so we want to make predictions. And so this is like went back to my files. This is like a prediction we made in August 22. Yeah, August 22nd. So this is the data we had, and this is the model we fitted. So the data doesn't indicate. If you look at the data, you don't see it's going it's going to go down. We don't know when it's going to go down. The model predicts that it will go down, let's say, in the middle of September, to the start of September. Okay, in this case, the prediction worked out quite well, and just to show, sometimes the predictions work, and it did go down, and the peak was around what the model predicted. This is the fit to the various groups. Now I want to discuss what we can do. Okay, beyond trying to make predictions, what can we do with this, like retrospectively? So we have the fitted model. We fitted the model to the data. We can consider all sorts of like counterfactual scenarios, and maybe learn something. So the green line here is the dots are the real data. The green line is the model after being fitted to the data. This is already data up to the start of October. And so decline has already begun because of the boosters, and we can just run the model again, but now remove the boosters, so we can see what would have happened, at least, okay, according to this model, if boosters had not been given. Okay, we would have reached a peak of 10,000 per day. The population of Israel is 9 million. Okay, we would have reached 30,000, which this would have led to a lockdown before this point, but okay, we can see the effect of the booster campaign. We can also check what would have happened. There was a lot of discussion also, in the UK about age groups, who to give boosters to. We can see that if we had vaccinated only the 60 plus group, then we still would have had a very nice effect from this booster campaign. Okay, but if you vaccinate more, then you get better results. Another thing you can do is check or estimate what would have happened if the timing of the booster campaign had been different. So here the blue line is the actual curve of infections according to the model, which fits the data, and the higher curve is the if the booster campaign was started 2 weeks later. 2 weeks later than it actually did start. So, okay, it's not surprising that we would have had many more cases, because it's a competition between the booster campaign and the epidemic. The epidemic was going on, so it could have been much worse. If we could start 2 weeks earlier, then we would have gotten much better results, of course. Another thing, of course, we want to we can now think about what's expected in the future. So at this point, we're down to a few hundred cases per day. But what about the next wave? So the big unknown here is the waning of the booster. So it seems there are indications that the booster is working better than the original 2 shots. It's giving better protection, but will it wane slower or not? This is something that we don't know. So here are 2 scenarios. One, the blue one is the waning is the same. If we assume the waning of the same rate as the original vaccine, so then we expect the next wave sometime in the spring, early summer. If it wanes at half the rate of the vaccine, then we expect the next wave sometime in the fall. another thing in the bottom part here, you see this is if the waning is the same, but looking at different scenarios for the timing of the booster campaign. So what we see here, okay, if we saw before that if we had started the booster campaign earlier, then we would have had a much smaller epidemic if we started 2 weeks earlier, but there would be a price to pay because the next wave would be earlier and let's say higher. This is because during this epidemic we gathered some herd immunity. So if you don't have this epidemic, then the next one will be earlier. Okay, so I think I will stop here because
you still have another 5 to 8 minutes. So
I can. I don't want to start a long story now, but I can say my third part, which I said, is that if time permits, thinking about what will happen in the future, I'll just say just a few words. So that if you look at the SEIR model, then it shows it gives an epidemic which ends. And then nothing more happens. If you want, but no one thinks that the coronavirus is going to disappear at this point, anytime in the foreseeable future, and that's because if we want to understand what will happen, we have to add the mechanisms that renew the susceptible population. And this is either births or the waning of infection-induced immunity, and or evolution of new pathogens. But even if we just have birth, even if we just add birth to our model, let's say immunity is forever. Whoever gets sick doesn't get sick again. If you add birth, this already leads to what is called an endemic state, an endemic equilibrium, through a series of smaller and smaller epidemics, gradually converging to some steady state, which will be an endemic state, and then the pathogen will persist forever, but at some low level. What I did is you can look at also in a phase plane picture. I did some back of the envelope calculations. So in this scenario, you can compute the steady state here explicitly. It's just solving some algebraic equations. The steady state for I assume the 1.5% birth rate. These are parameters which are okay for corona. They fit the coronavirus. And what you get, let's say, if you take the population of the UK, you get a prevalence of 15,000. So 15,000 people will be infected at any time in this endemic steady state. So it means that 750,000 per year will be infected, which is not a big deal. And it's especially not a big deal if you think about the fact you can also calculate that 75% of people will be infected within their lifetime, and you can also compute the average age of infection, which will be 16, and that only a very 3% of the people will be infected by after age 50. So assuming that that most people will be infected before age 50, and the disease is not dangerous, this is not such a bad scenario, even even without vaccination. If you add this waning of immunity, now I'm talking about immunity induced by infection. So now looking at other coronaviruses which are endemic in the population, it seems that it might be that the immunity induced by disease will last for about 3 years. If you put that into the model, you have what is called SIRS model. So you return from the recovery to the susceptible after 3 years, then you get a much, again, you get an endemic equilibrium after some years, like you see in this picture. But then if you do the calculation, you see it's a much higher equilibrium. You get like at any time, 0.5% of the population will be infected, which means that each year, 25% of the population will be infected each year, which it's like influenza. Influenza is about this level. But on the other hand, because it will be so strong, the average age of infection, the primary infection is something like 1 year. And the fraction of people who've been infected for the first time at age over 50 will be negligible. So basically everyone will be infected when they're young, and then they will hopefully be protected from the more, they will be reinfected, but they will be protected from the more severe, because this is under the assumption that the prior infection protects from the more severe outcomes in higher ages, which is what happened with the other coronaviruses, which are just causing mild cold. So this is kind of the calculations that I want to show. There's more things that can be said about seasonality, chaos, and other things if you want to complicate these simple models a bit, but I think I should stop here. If you have any questions, I will be glad to answer.
Thank you, Guy. Thank you very much for a very, very interesting talk. So if we were physically present, we would be clapping now, but I'm sure everyone is. So we have about 5 minutes for questions. So if anyone in the audience have any question, please unmute yourself and put on your camera if you can and ask away.
Hello.
Hi.
No raising hands, I guess, Maciej, right?
No, please ask away. Yeah.
Okay, so thanks a lot for the talk. It's very, very interesting. And do I understand correctly that especially the latter part was in direct collaboration with the Israeli government? How did it work, your collaboration with them?
Yes, we were advising the Israeli health ministry.
And so they came to you and asked for this modeling, or you thought to do this model? And I'm asking because we also have some collaboration here with the government, and was wondering about modes of collaboration. There's a lot of discussion about what's the most efficient way for policy making recommendations to be absorbed. And I'm sure you have an idea after having been in touch with them over months.
Yeah, so it is very, everything is smaller, and we don't have, like, the UK has a very strong tradition, I think, in epidemiological modeling, and we don't have it. So I think we're basically the only modeling group in Israel. So my collaborators from this are working in this institute called the Gertner Institute, which is affiliated to the Ministry of Health. So they're already inside this system.
Mhm.
I've been collaborating with them, and less directly. So they were presenting, giving these presentations to the officials of the health ministry, but so sometimes they can. I mean, they often come with questions. So they want to, for example, for this booster campaign, they wanted to have some estimates of how it would go, how it would do.
Mhm.
So,
Okay.
the questions came from them, and they use what they found convenient, let's say.
Okay. So yeah, you make some recommendations and then they pick the parts that.
Yeah. Well, yes. There's a lot of and also the position of the Ministry of Health was not that of the other parts of the government. They were the most, let's say, they wanted the strict measures and so forth, but political haggling. So
Okay.
at some point they use the models to show that, okay, this is going to
But
do something soon, then it's going to go badly.
Yeah. Okay, thank you.
Can I ask a question that's a bit between philosophy and mathematics? So we're living in this sort of dynamical system, right? And in the early months, you could easily, or rather easily, say what will happen, just exponential growth or exponential decay if you have a lockdown and so on, based on this R number and so on. For t going to infinity, as you show, you can say some things, but now we are somehow in this regime between the small t and the large t. So how can you determine when you transition sort of from one regime to another regime? I'm asking this in the context, so in England, we're in Wales, but in England, sort of all measures were removed in the summer and so on, in sort of signaling that, at least my understanding from a mathematical point of view, that we are in the t going to infinity regime, and so you can behave as if it's all done because we are in the asymptotic regime. But that's somehow forcing something that perhaps is not true. So when do you know that you've entered somehow into this asymptotic regime?
Good question. In the model, you can simulate the whole. You can simulate both the near future and the far future. Is easier to study analytically because you have this equilibrium. But okay, so it really depends on the details of the model. If I look at this simulation here with the waning immunity after 3 years, then it's already after about 10 years. It seems already in the asymptotic, like in the equilibrium.
So I guess my question is: so you have the oscillations initially. So to what extent are these oscillations dependent on, as you mentioned, stochasticity? So to what extent? So the asymptotically, what happens shouldn't be influenced by all sorts of random events, right? But these oscillations can probably be very much influenced by random events. or no?
Question. I'm not so sure because okay at the local level of it's true, but some sense okay we have we run stochastic models of various sorts, and okay the most extreme form is like this agent-based modeling where you represent each person as an individual. If you do that, it's a very heavy computational thing, but often you will see that the stochastic models, when you have a large enough population of, let's say, even several thousands, the stochastic model behaves like the deterministic model. Just so I mean, these oscillations are related to build-up of susceptibility and epidemics, and so it's I'm not so sure that stochasticity is a crucial element, but maybe I have to think about it. Think about it more.
Okay, so I think it's a good point to stop, so we can actually stay in the channel for a bit longer for a more informal chat. So if there's any other questions, you can ask them later. But I just wanted to take this opportunity to thank Guy again for a very, very interesting talk. We really enjoyed it, and thank you again for accepting the invitation. And to everyone in the audience, thank you for joining this week. We'll be meeting next week for an in-person seminar, and I'll send an email about it later this week. Thank you very much again.
Thank you very much.